Welcome to episode 57 of Fresh Thinking by Snowden Optiro. My name is Oscar Rondon. I'm a principal geostatistician with Snowden Optiro. And today I'm joined by Ian Glacken, who is an executive consultant at Snowden Optiro. Ian is a geologist with postgraduate qualifications in geostatistics, mining geology, and computing, who has more than 35 years of experience. I'm going to get this short here, and otherwise I'm going to start talking about all your experience during this 35 years.
That's okay,
so
Oscar.
the topic of the podcast today is top-cutting strategy for resource estimation. Thanks for joining me, Ian.
Thanks, Oscar. So what I'd say about top cuts is some people swear by them, other people swear about them. So let's explore this over the next few minutes.
Let's go. Ian, can you please describe what a top-cut strategy is and why it's needed in resource estimation?
Sure. So what I should say straight up is that some people know it as top cutting, some people know it as capping. It's essentially the same thing. What we're doing is, as I'm sure most of you know, is we're choosing a threshold or thresholds, and we're resetting grades above that threshold to that threshold. So we're not getting rid of any data. We're not censoring the data. We're simply cutting or capping the data. So why do we need a top cut strategy? Well, a number of reasons. We may have a situation where we've got a small number of high grades in a sea of low grades. And when you do an estimation, depending on your search ellipse, you might end up smearing or smoothing those high grades into the low grade areas. And depending on the contrast between the high grades and the low grades, you might end up overestimating the grades or underestimating them as well. So that's one of the main reasons. Another motivation for doing top cuts might be is if you have a relative bias in the assaying. Let's suppose we're looking at gold, and if you have a gold assay, it might be 50 grams, it might be 60 grams, it might be 70. In other words, the relative precision is quite low. So it's quite high relative precision. So what we would do is we would maybe tamp that down a bit. And then the other main strategy or main reason for using top cuts is that we have a excessive amount of variability in our domains. And this might be a function of poor domaining. It might simply be a function of the nature of the mineralization, typically precious metal mineralization, but it could be anything. So there's 3 or maybe 4 motivations for applying top cuts or caps.
Thanks, Ian. It is clear now why we need top cut in practical application. But Ian, can you please comment on what approaches do we use for selecting a top cut value?
Yeah, so what I would say, Oscar, is that these approaches vary from simple to ridiculously complex. And what I would also say is, and we'll talk about this later on, there actually is no theoretical basis for capping or top cutting. However, it's a very pragmatic approach, and sometimes it works. So what sort of techniques can we use? One is looking at the coefficient of variation, which of course is the relative standard deviation. And we would apply a cap or a cut value to achieve a certain target CV or coefficient of variation. Now that might be 2 or 1.8 or whatever. And so that's one approach. Another approach is looking at the percentile of the cap value. So a good rule of thumb here is that if you have a top cut that's more severe than, say, the 97th percentile or maybe the 97.5th percentile of the distribution, then you're probably cutting it too severely. Before I go any further, one thing I just want to say is people talk about high top cuts and low top cuts. I find that very confusing. What I would ask people to talk about is optimistic top cuts or conservative or severe top cuts. So in other words, a severe top cut is when you're cutting the data severely. An optimistic top cut is when you're not cutting it very severely. So we talked about CV, we talked about the percentile. We could also look at, say, the reduction in the mean value from the uncut data to the cut data. And typically we would be looking to reduce the mean no more than about 15%. All of these are just rules of thumb, and there are exceptions. Another one that's quite useful is this idea of what we call disintegration analysis. Now, disintegration analysis is where we look at the relative percentage difference between we sort the data from high to low, and then we look at the relative percentage difference between the highest and the second highest and the third highest, and so on. And what we're looking for is a point at which that that percentage difference becomes quite small. And that may or may not indicate a second population. Now, there are a number of techniques that very similar to this that use a log probability plot. And the idea is that you look for inflection points in these log probability plots. Now, again, these are assuming that you have a high-grade population of mineralization, whatever it is. There's a whole range of logarithmic approaches. I wouldn't touch these with a barge pole, because when you're using logarithmic approaches, you're making some pretty strong assumptions. And then I mentioned that some of them are very complicated. There are a range of applications or methods that use simulation for top cuts, and they consider this idea of what's called metal at risk. So there's a lot of applications. And I guess the key point here is to look at a range of types of top cut and to see whether you get some consensus or similarity between those various approaches.
Yeah, and you quickly mentioned some of the techniques, but I would like to take this opportunity to mention a technique that is available in Supervisor, because all the techniques you discuss are based on the statistical distribution of the data. One key technique could be to look at the metal content in the drill holes and see how the top cut value impacts the metal content. That's another approach and is already available in Supervisor. Thanks for that, Ian.
Thank you.
Look, my next question, Ian, is quite controversial, as you mentioned at the beginning. So I know that some practitioners are very critical when it comes to use and select a top cut value. Can you comment on why and what are the alternatives to the approaches that you mentioned?
Sure. What I would say is the reason that some practitioners are critical is that, as I mentioned earlier on, there's absolutely no theoretical basis for a top cut. So some people, very theoretical, would argue, well, the data is the data. We don't need to top cut the data. Now, having worked as a mine geologist for many years and having reviewed many resource estimates, I would say that in some cases, not applying a top cut or a cap can be a fatal mistake. I did go to an operation many years ago, and it was a very high-grade gold operation. I won't say where it is, but the difference between applying a top cut and no top cut was amounted to 750,000 ounces of gold. So in this operation, the top cut value was critical. Now, having said that, one thing you should always do is look for an alternative to a top cut. So when I present this as part of a training course, I always say to people that you should look for the alternative. So the alternative, which is an obvious answer, the alternative is to subdomain the high grades. In other words, to see if your high grades can be joined together, creating a subdomain or several subdomains. And of course, if you manage to subdomain the high grades, then you've got a high grade population. It doesn't look at the low grades, and you don't need to apply a top cut. So you should always look for that alternative, subdomaining the high grade, or in some cases, subdomaining out the low grades. Now, if we see that a domain has been interpreted rather poorly, let's say, someone's just put an outline around the grades and all the high grades and the low grades are mixed in together, then one solution, rather than applying a top cut, is to look at this idea of subdomaining. Otherwise, you have what we're looking for if we think of the domain as a current pudding. In other words, we've got high grades in among the pudding. What we're looking for is to join the currents together, if you like. Now, that may or may not be possible. In some cases, it works quite well. In other cases, it's not possible. So that's the first thing I would say. Always look for the alternative, which is subdomaining. The other approach, which is available in a lot of software, including Datamine, is this idea of high yield. So the idea of a high yield is that, as we see in most ore bodies that are high grade, the high grades have a relatively low area of influence. If we're talking about gold, the high grade gold might have an actual mineralization area of say 10 by 10. So what we can do in most software these days is we can define this high yield or high limit. In other words, what we're saying is that once we've chosen a high value, whatever that might be, above 10 grams or 20 grams or so on, that has a relatively small area of influence. So in other words, let's suppose we have a threshold at 20 grams per ton, 30, 40, 50, those grades have a very limited area of influence. And again, this makes absolute sense if what you're seeing is restricted, small, high-grade zones. Now, there are ore bodies where you have a genuine high-grade trend, and of course, geologically, you need to identify that. And if that's the case, then this high-yield approach it isn't going to work. So that's another approach. And then another alternative to cutting is an indicator approach. So gets a bit complicated, but the idea here is that you would choose an indicator. An indicator is a threshold. It's a cutoff, if you like, between the high grades and the low grades. So let's suppose, again, we're talking about gold, and we might have an indicator at, say, 30 grams per ton. In other words, what we're doing is we're effectively taking samples that are above 30 grams per ton, and we're giving them a 1. And we're taking samples below 30 grams per ton and we're giving them a value of 0. This is the well-known indicator transform, which hopefully you're familiar with. Now, if we estimate those 1s and 0s, what we end up getting is the proportion of either the high-grade population, in other words, above 30, or the proportion of the low-grade, depending on which way we assign the indicators. So then what we would do is we would carry out, let's say, ordinary kriging on the low-grade population, and then we would weight that by the proportion of the of that low-grade population in the block. And we might use another estimation. We might just use ordinary kriging with the high-grade population, and then we would weight that with the proportion of the high grade. So in other words, what we're doing, of course, is we're greatly reducing the impact of these high grades. Now, if your high grades are restricted spatially, as I mentioned, and you generate the variogram, then you will see, hopefully, that the range of the variogram is quite small. In other words, the high grades are limited. So I like that approach because it considers the geology. I like the high yield approach because it considers the geology, and I like the subdomain approach because that considers the geology. So I would always ask people, think about those alternatives before you jump straight into a top cut.
Correct. Yeah, look, I like your explanation. It's quite clear. Thanks for that. But my takeaway is that no matter what, we need to deal with extreme values. We can do it, let's say, using the drill hole data with the top cut strategy, or at the resource estimation stage with the indicator and the high yield, which is great. Thank you, Ian. Ian, some practitioners claim that reconciliation provides a suitable guide for selecting the top cut value. What are your thoughts regarding this?
This is a very interesting question, and there's no question that in the past, people have attempted to improve their reconciliation by applying a very severe top cut. When I first started, one of the geologists that I was working with, they did this on a regular basis, and they were aware of this. So in other words, they were manipulating the top cut to get a better reconciliation. But having said that, in recent years, I've seen examples more sophisticated examples where people have actually used the top cut and then the reconciliation to calibrate the top cut, or rather to calibrate the reconciliation. Now that can be fine, but what you need to consider is, when we get onto reconciliation, and we could talk for months about this, but when you get onto reconciliation, the reason for a good or a poor reconciliation is not simply the grades. It might be the truck tons or the moisture or stockpile errors or whatever. In other words, you're correcting something that doesn't need to be or shouldn't be corrected. So while in principle, I like the idea of calibrating the top cut using the reconciliation, and in some cases I've seen this done really well, you need to be very careful that you believe your reconciliation. And it is based entirely on the resource model, not on some other feature, which is sometimes the case, but mostly not the case.
Okay, thank you, Ian. That draws the podcast to a close. Thank you for joining me on this chat about an important topic that is top cut.
Thanks, Oscar. Good to talk to you.
If you would like to listen more of the Snowden Optiro podcast, you will find them in the podcast platform like Spotify, Google, and other podcast platforms. Thank you for joining us.